It's my pleasure to introduce Jeff. The structure of the talk, so roughly he'll probably go till maybe 10 after, quarter after, and then there'll be lunch out there. We encourage people to stick around and get to know other people out. So I would say Jeff's known as the father, or some might prefer the godfather of machine learning, particularly deep learning. And despite what you might hear in the popular press, it's deep learning hasn't just sprung out of nowhere. He's actually been working on it for over 30 years now, and some of us have been working on it almost as long. And he's responsible for some of the original algorithms, but more recently, very importantly, all of the techniques, or many of the techniques, I would say, that have allowed these models to work on very hard, very large problems really have their origin in Jeff's ideas, so he gets a lot of credit for that as well. And he's won tons of awards from many different spheres, things like the Rummel Prize in Cognitive Science, and just this year he won the Clerk Maxwell Award in IEEE. He's won the Hertzberg Gold Medal in Fellow of the Royal Society. So, and his students and postdocs that have worked with him reads like a who's who in machine learning. Just about everybody who is a name in the field now, either in academia or in industry, spent time here, either significant time, likely either as a student or postdoc. All right, so, and on a personal note, I've had the pleasure of working with him. I was a grad student with him, went away and then came back, and then have worked down the hall for most of the last 15 years. And I'm looking forward to more of the same. I'm hoping he's spending more and more time in Toronto, and I'm looking forward to him coming into my door and telling me how he's just figured out how the brain works many more times. So, take it away, Jim.
Hi, I'm Jeff, and I'm a machine learning fossil. And I'm going to prove it to you. So I'm going to talk about an idea today that I started working on in 1973. And the idea is that you can store temporary memories not by having a bunch of neurons sitting around active, storing those memories like most neuroscientists think, but by having temporary changes to synapse strengths. It's a fairly obvious idea, but it's been very little explored. So the basic idea is on each connection, we'll have your standard slow weight, and that adapts slowly, and that's where your long-term knowledge is. And we'll have a fast weight, and that adapts rapidly, and that allows states that occurred recently to become attractors, as you'll see. So it adapts rapidly and decays rapidly. Some evidence that we really have things like that is priming. If you hear a word and then half an hour later you're given the same word in a lot of noise, so much noise that you wouldn't normally be able to recognize it, you'll be able to recognize it. That is, your threshold for recognizing it has gone way down. Now, if you had localist representations, 1 neuron per word, you would just lower the threshold of the neuron, and that will be a way to achieve that effect. But if your representations are distributed patterns of activity, you might try and keep that faint pattern of activity around, or you might change the weights between neurons in that pattern of activity so that pattern of activity becomes a stronger attractor. And that's actually how we store long-term memories anyway. You change weights to store these patterns. You don't actually store the patterns. So why don't we store temporary memories like that? Okay. So I'm now going to describe... I just need to tell you why that's better than activity vectors. If you think about storing memories in temporary changes of the weights, you've got far more capacity. It's n squared versus n if you've got n neurons fully connected. You've still got a lot more capacity, even if your storage rule is a very inefficient storage rule. So there's a lot of work in neural nets on trying to find efficient storage rules. But for this purpose, we don't need to store more than like 100 temporary things, let's say. And so if we've got 1,000 units, you can easily store 100 attractors just with simple one-shot learning. By one-shot out-of-product learning, I mean, if you want to make a pattern more stable, what you do is you take pairs of units that are active and increase the weight between them. And maybe an active one and an inactive one and make the weight more negative. So basically the Hopfield learning rule, which has sort of gone out of favor recently. People have lost interest in it. But it's actually a very good learning rule for temporary memory. It's not a good learning rule for long-term memory. So you can think of three ways of storing temporary knowledge. In an LSTM, a long short-term memory, a recurrent net that's designed to be able to deal with long-term regularities and sequences, the knowledge about the sequence so far is stored in the activities of the hidden units. And that's a limited capacity system. You can't store many vectors there because you're superimposing vectors. If you think about trying to store some independent vectors there, and you want to store them accurately, you can store one. If you store more than one, you're going to get interference. Also, if you've got a memory from some time ago in the sequence, and what you're doing at present doesn't involve that, that's interfering with your capacity for processing at present, because it's affecting the states of the hidden units. You've got to somehow keep that memory around, but you don't need it right now. Okay. So fast waits are a way of storing information about what's happened recently without interfering with, without using up the capacity of the hidden units to do processing, without using up the capacity of the hidden vectors. And what they'll do is states that you've had previously will become stronger attractors. What's more, if you now go to a state that's close to the one you had previously, you'll be attracted towards the previous state. And so you can sort of, if you're going to settle into an attractor, you can flavor where you settle based on what you had previously. So, now we're going to flash back to 1973. This was actually the first talk I ever gave, and it was an utter disaster. At the end of the talk, no one had a clue what I was talking about, but they were all very confident that it was a complete waste of time. So neural nets then were known to be useless because Minsky and Papert had proved it in 1969. It was known they could only learn simple associations. And if you're in AI, it was obvious they were a waste of time, partly because of the prevailing ideology that AI was all about software and the hardware didn't matter, so why could the brain possibly be relevant? Ask NVIDIA about that. Actually, that was the main reason, but there was another reason, which was that people thought neural networks couldn't do things like recursion. So the sort of favorite things we do in Lisp, the neat ways we solve problems in Lisp, you could never do in a neural network, and therefore forget neural networks. So when I started graduate work, that was the prevailing ideology. So obviously the first thing to do was show how you do recursion in neural networks. It turned out that was very politically naive. If people have decided that something's useless, if you show how you can solve a problem with it, they're not interested because it's useless anyway. Okay, so to do real recursion in a neural net, you need to be able to use the same neurons and the same weights on a recursive subcall. So for example, if you're processing the sentence, John disliked Bill because Bill was rude to Mary, when you're processing Bill was rude to Mary, you need to be using the very same neurons and the very same weights as you were using for processing the whole sentence. And there's an obvious problem, which is you're halfway through processing the whole sentence. So what happens to all the processing you've done so far? You obviously have to store it somehow. Now, a normal computer scientist would say you need a stack. And very recently, in the last few years, computational linguists have been exploring how you implement stacks with neural nets. And they've done it the sort of obvious way of saying, well, we'll store some activity vectors, and then we'll access those stored vectors. But if you think about the brain, I don't believe you store copies of neural activity vectors. I want to do it with fast weights. So what you need to do while processing that sentence is store what you've done so far, go off and use the same hardware for processing the embedded sentence, and then come back, take the processing you've done on the embedded sentence, sort of condense it into something that'll fit in with some larger thing, and then retrieve where you were in the higher sentence and add in this new information. And that's what I want to do with fast weights. So, I'm going to describe the program I wrote in 1973 that failed to convince anybody. But the idea I'm going to talk about today is pretty much the same, except that we now know how to backpropagate to learn hidden representations. Back then we didn't know how to learn hidden representations, so you had to design them all by hand. So I'm going to start with a simple non-recursive task. And the machine I'm doing it on has 64K of memory, but that's okay because it has virtually infinite memory because it's got a megabyte disk that has virtual memory. And this 64K memory machine is shared by 40 researchers. Okay. That's why you needed the megabyte disk, so you don't run out of memory. Okay. So the task is, I'm going to give you I'm going to give you the identity of a capital letter, and I'm going to tell you its pose, and then you're going to have to tell me a sequence of specifications of the strokes I have to draw to create that letter. And the neural net that's going to do it is going to consist of groups of neurons, and each group of neurons is going to have a number of alternative states, so more than 2 states typically. And the way the process is going to work is each group of neurons will be in some particular state at present, and that state will have some weights to all the states of all the other groups and itself. And so what you'll do is you'll take the current states, they'll provide inputs to the states of all of the groups, you'll see which state gets the biggest weight, and that'll be the state of that group. So it's what you might call a hard max. You just make a hard decision. It's a very sort of simple idealization of how groups of neurons might work. But I made it work. So I designed some training sequences, and the training sequences look something like this. This thing here is the program counter, and this is doing a non-recursive task. So the first state is saying the identity of the letter I want to draw is a T. I want to draw it in an orientation of plus 90 degrees. I want to draw it in this X position and this Y position. And now what the neural network has to do is produce a sequence of specifications of strokes. And when it's specified a stroke, it has to say, now do it. So this is the sort of pen down. And the green stuff is the specification of strokes. So the strokes can be horizontal or vertical. And it tells the position of the center of the stroke. So the X position of the center is 5 for this one and 3 for that one, and so on. And so if you step through this sequence of states, if I've managed to train the neural network so that sequence of states would be followed by this sequence of states, and so on, then what it would do is this. It would go to this state, and it would draw a vertical stroke at x coordinate 5 and with the center x5 and y4. And then it would draw a horizontal stroke centered at 3, 4, and then it would be done. So that's non-recursive. And the computation obviously consists of taking this plus 90 in these positions and figuring out where to put the strokes. But it's not impressive by current terms because all of this was designed by hand. I figured out what states to use, and I just hoped I'd be able to learn weights that would achieve that. I'll come back to that issue in a little while. But now let's make it recursive when it gets interesting. Oh, let me tell you how it's trained. At each time step, if you get the right state for a group, you don't change the incoming weights. But if, with your current weights, you get the wrong state, what you do is you decrement all the weights that led to the wrong state, and you increment all the weights that would have led to the right state. It's the perceptron convergence procedure, but for multi-state units. In 1973, I got very excited because I generalized the perceptron convergence procedure to multi-state units, and I wrote my first paper. The paper was written on a machine, I'm sorry about this. The paper was written on a machine that had a paper tape so that you typed, but it punched a paper tape. If you wanted to correct, you had to start again at the beginning and go back and make a new paper tape. And if you went one character past where you wanted to correct, you had to go back to the beginning and make a new paper tape. So I still remember writing that paper. And I wrote the paper and showed it to my advisor, and he said, now in a paper you ought to put references. So I'd read Minsky and Papert. So I looked around for other machine learning books, and I read a book by Niels Nilsson called Machine Learning. And in the middle of the book, he had my algorithm. he said the perceptron convergence procedure is easily generalized to multi-state units. So, that's life. Now we're going to make a recursive version. We're going to define a capital letter I as a capital letter T with a stroke across the bottom. And so to draw an I, what you have to do is first draw a T, and then you have to draw a stroke across the bottom. There were several other letters too. Now, when we draw the T, we want to use exactly the same neurons and weights as we were using for drawing the I. So we're going to have to remember about the I when we draw the T. And we're going to use a fast associative memory for that. We're going to use an algorithm that says whenever two groups are active together, you increase a fast weight between them. And this is a weight that decays quite fast. That's why it's a fast weight. And you increase it whenever two. So it's purely associative learning. It's not error correction learning. It's just sort of Hebbian learning. And that's going to be happening all the time. And then we're going to try and train it with the perceptron convergence rule, given that this fast associative memory is going on all the time. And we're going to hope we can get the right kind of behavior. And of course, we're going to have designed the sequence of states we ask for to make it easy to get the right kind of behavior, as you'll see. So here it is being recursive. You tell it, I want you to draw an I at this orientation. And it says, OK, I want to draw an I at this orientation. The very first thing I have to do is draw a T, and just by coincidence, that's exactly the same parameters. It might not have been. This might have been different parameters that you had to compute from the parameters here, but it just happens that the T has the same pose as the I. So now I've got to draw the T. So notice it's replaced this representation by this representation. And now it draws the T as before. And when it's finished drawing the T, it knows this is the last thing in a T. So now what it does is, because this is the last thing in the T, this causes all of these units to go into a state I call question mark. It's a kind of neutral state. It's basically erasing the current state and sort of leaving it open. But it also causes, the program counter to go up one, to go back a level. Now, when you're at this level, with level 1, you associated all these values. So because you've gone back a level now, if you ask what's going to happen here, the slow weights don't have anything to say about this. All these states are zeros, and the slow weights sort of don't know what to put there. But the fast weights know that associated with a 1, the level 1, is all of this stuff, and so they fill in all of that stuff. Now what you've done is you've retrieved where you were here, including the sort of wrong setting of the program counter. So now what you have to do is notice that you just did a pop. So that's what this is doing. Notice I added this. After this stage, it says I've just done a pop. And if it's just done a pop, it has to increment the program counter. That's the one extra thing it has to do, so that was a bit fiddly. Now, I should say, I'm not quite certain this is exactly what the program did, because this is from memory, and this was 43 years ago. But it was something very like this. And if you design it by hand, so that it can do these recursive calls, and you ask it to do these sequences, pretty soon you discover it can't learn it. And that's because you've asked it to do things like this. You've asked it from state 0, 0 to go to 0, 0, and from 0, 1 to go to 0, 1, and from 1, 0 to go to 0, 1, and from 1, 1 to go to 0, 0. And that can't be learned with any set of direct weights. That's your XOR problem. And the way to solve the XOR problem now is to have hidden units. Back then we didn't have hidden units. So what I did was I had temporally intermediate states. I had these groups that could have more states. So I would introduce extra states for a group that were kind of transitional states that allowed you to make things linearly independent. So if you take, for example, this second group here, and you give it 2 more states, called 2 and 3, Then you can ask it to do this sequence. So there's this sort of temporally intermediate stuff going on. And this sequence now makes things linearly separable. So that was how I solved linear separability, by just giving extra states rather than extra hidden units. And the whole thing worked, and I explained it, maybe not quite as clearly as I just explained it now. And nobody had a clue what I was talking about, and in particular, they didn't have any clue why you would want to do that. And anyway, it's pretty pathetic what it does. This was at the same time as Winograd was taking sentences that told you what to do with blocks and moving the blocks around. And this didn't seem quite as impressive. And so that was the end of that. But 43 years later, neural nets are no longer useless. And so people are interested in how to do recursion. So here's the update. It turns out you can make a very good career by just recycling ideas you had a long time ago. Slowly. So let's use RNNs with rectified linear units. These are simpler than LSTMs. And just straight RNNs with ReLUs tend to blow up, and they don't work as well as LSTMs. If you initialize them with the identity matrix, which we started doing about 2013, then they hold information much better. They're still not quite as good at LSTMs, but they're getting to be in the same ballpark. And because they're nice and simple, that's what we're going to use. So here's a simple RNN composed of rectified linear units. You have a layer of hidden units, some input units, and some output units. And now I'm going to show you a simple RNN that's identical to this one. That is, behaves identically to this one, which might seem stupid, but you'll see why. We can make something that behaves identically like this. We take the input that goes to these hidden units, both the input from the previous time step and the input from the input, and we just replicate that input to the next time step. And we put in the null matrix here. That's just a bunch of zeros. So really, we're just doing at this time step exactly what we did at that time step. We're just doing it again. So we've doubled the amount of computation for no good reason. But it will behave the same way. And obviously, if this isn't the null matrix, something interesting might happen. So now what we're going to do is we're going to use an outer product learning rule, which says that every time we get a hidden state, like this, we're going to learn fast weights. That is, we're going to take the outer product of that hidden vector with itself and add that to the fast weight matrix and decay the previous weights. So the fast weight matrix will actually, at any time, it'll be the sum of contributions from the past, with the contribution declining with time. And these contributions will all be outer products. Okay. So now, these weights will cause this hidden state to be different from this hidden state, because you'll have taken this hidden state and done some retrieval, and if there's other hidden states that are similar to this one in the past but a bit different, it'll make this hidden state a bit different from that hidden state. Now, this didn't work very well. So we added something that made it work much better. This was Jimmy Bar, which was layer normalization. So the idea is that at each time you produce a new state, instead of taking the inputs to the hidden units and putting them through the nonlinearity, you take the inputs to the hidden units, you normalize them to have zero mean and unit variance, and then you put them through the hidden units. But before you put them through the hidden units, you add to each hidden unit, you add a gain and a bias that's specific to that hidden unit. So they can have gains and biases. So when you did the normalization, you didn't throw away everything about scale and offset. You're going to put it back in again, and then you have to back propagate properly. So the people who did batch norm realized this is what you should do when you normalize across the state of a hidden unit across a batch. We're just rotating batch norm and doing it for a layer instead of a batch. And that works much better in RNNs, because now you can do it as the RNN is running separately each time step. Okay. Jimmy Barr and Jamie Kiros have shown that this makes learning much faster in relo RNNs. It's also kind of crucial for making this fast associative memory work nicely. Basically what it does is it makes the hidden state vectors be roughly the same length as each other, if you assume biases and gains are small. Where by small for a gain, I mean close to 1, because I'm in a math place. So close to the identity operation. So here's a toy problem to test out that really ought to work. We're going to have an associative memory task. You give it a letter and a number and a letter and a number and a letter and a number and so on for a while. And then you say, I'm going to ask you a question. And you give it a letter, and it has to give you back the number. And so you can try training, and these are arbitrary associations. So you train it on a lot of data, thousands and thousands of cases, but the associations are arbitrary. So it knows that a number comes after a letter, but it doesn't know which number in general. The slow weights can't hold that information. All the slow weights can do is hold information telling it how to represent things, so that now the fast weights are going to be able to solve the problem, to store the memory. And when we train it, we backpropagate, including backpropagating through the associative fast weights. So the way the fast weights work is very simple, but when you backpropagate, you take account of the way the fast weights are working to get derivatives. So you're getting the true derivatives. And because you're taking account of the way the fast weights are working, you'll tend to generate representations such that, given the way the fast weights work, using those representations, you'll be able to get the right answer. So in particular for this task, it would be a really good idea if when the net saw a letter, it sort of put a representation of that letter in one part of the hidden state, and then when it saw a number, it put a representation of that number in another part of the hidden state, keeping the representation of the letter. Because then the fast associative memory would associate together the representation of that letter with the representation of that number. And then later on, when you put in C, the fast associative memory would make C lead to 9. That is, the vector for C would tend to evoke the vector for 9, the hidden state for 9. And so you train it up, or rather Jimmy trains it up. It turns out there's a sort of variable in all these things. There's the idea and there's the student who did it. And the student who did it is much more important than the idea, but there you go. Jimmy first took the input symbol and turned it into a 100-dimensional embedding vector. That was for obscure reasons to make it similar to something else he was doing. So don't worry about that. It doesn't seem like a sensible thing to do. You just have to trust Jimmy. This was so he could compare with something else. And you do the same at the output before you go to the softmax. And then you compare an RNN where the weights are initialized with the identity matrix with varying numbers of hidden units and see what error rate it gets on this task. And an iRNN can solve this task with 100 hidden units. It can store enough information to have remembered the whole sequence so far in the hidden states and get the right answer. An LSTM can solve this task with only 50 hidden units. And an associative LSTM is epsilon better than an LSTM. I'm not going to talk about that. A fast weight RNN can solve this task with only 20 hidden units, which isn't surprising because with 20 hidden units, it's got a much bigger memory capacity in the fast weights. The issue was, would it learn how to use that memory capacity? And the answer is yes. It's obviously learned how to use the memory in the fast weights to solve this associative retrieval task. So that's just a kind of initial experiment to demonstrate that the idea works. Now we're going to try it on something much more interesting, which is using fast weights to combine glimpses. So here's a theory of how vision works. It happens to be correct. It's my theory. We think you see the whole image at once. And computer vision used to take an image and put it in. But there's all these phenomena that show that's not really what happens at all. To first order, vision consists of sampling, and when you sample, you take a very small part of the image at very high resolution, and a bit more at lower resolution, and the stuff out there is extremely low resolution, though you are sensitive to movement out there, but for static stuff you know almost nothing about what's going on. And vision consists of a sequence of those glimpses. The eye is very clever, because by having the resolution decrease as you go out, you can zoom by translating. But if I want to zoom in on something, I just translate so my fovea is there, and now I've got the same thing at much higher resolution. So by just having these 2 degrees of freedom, you get to do position, but you also get to zoom in on things, but only if you put them in the middle. Okay. So that's the outer loop of vision. The outer loop of vision is you look somewhere and you get this, I'll call it a retinal image, which is very high resolution for some parts of the stuff that comes in, the stuff that impinges on you, and very low resolution for the others. And now the issue is, how do we put all that together? And we're obviously extremely good at putting it all together. Just to impress on you how much vision is like this, I don't know if you can see this bit of the whiteboard here, but if you focus really hard, maybe not the people at the back of the room, you can see there's a little white piece of chalk there. And people quite close can probably see this little white piece of chalk is divided into, it actually is a solid line here and splits into 2 lines there. Now ask yourself how long it would take you to process the whole of the optic array coming in at that level of detail. It would take you a week. It would take you a week just to deal with this optic array. Okay? That shows you how much economy you're getting from just attending to important things. Of course, it means you can be fooled. If I can get you to attend to people throwing a ball, gorillas can walk through and you won't notice. So, we can obviously get a huge win if we can get 2 things. An intelligent way of deciding what to look at to solve a task, and we are very intelligent at that. If you're solving a task like driving, you're nearly always looking at just the best place to get new information. Occasionally you get distracted, but nearly always at just the best place. I've forgotten how that sentence started. But anyway, one thing is we need to look in intelligent places, and obviously that depends on the processing previous glimpses to decide where to look next, but in the context of a task. And the second thing is we need to integrate information over glimpses. So what we're going to do is break that apart and just try and solve one of those problems. We're going to suppose, this was a suggestion by Joel Lever at DeepMind, which was a very clever methodological suggestion, which was, if you get into where you look next, it's all very exciting, but you've got a reinforcement learning problem, and it's a tough problem. Why don't you just say, someone else told you where to look next? You have some fixed sequence of looking places. Just try and solve the integration problem. How do you integrate the information you got from these fixed places? So that's what we're going to do. One other thing about sequences of glimpses is they're not ideal for LSTMs, because an LSTM is for modeling sequences, and the actual order for a sequence of glimpses doesn't matter. The information conveyed by what you see with this sequence of glimpses is independent of the order. So the serial order is not conveying information here. You just need to integrate the information you got. So that makes it sort of ideal for this fast associative memory. So if you think, what do you get from one glimpse? What does the high up inferotemporal cortex in your visual system get from one fixation? Well, it's going to have bottom-up processing of that fixation. We're going to put a big convnet on it and bottom-up process it, and we're going to get what we got in that fixation. It's also going to get information coming from its previous state, the information that comes in a recurrent net. That's the immediate temporal context. But also you want to add in information that came from previous glimpses, particularly glimpses of subparts of this object should influence what you think about this object. If I'm looking at a face, and I just looked at the corner of the mouth and it's going up, but going up almost imperceptibly, but when I look at the corner of the mouth I can see it's going up, when I look at the whole face I can't, then when I look back at the whole face, I ought to be more likely to see a smiley face because of the information coming from the subpart that I just processed at high resolution. So the third source of information you want in determining the high-level inferotemporal representation. There's the bottom-up information from the image, which is the dominant information. There's the immediate temporal context from what you just saw. And then there's information stored about previous glimpses, particularly glimpses of parts of that object, which should influence how you interpret that object. And it's going to be important for things like recognizing facial expressions. So here's a sort of idea for how you might do that with fast weights. Let's suppose we first glimpse the whole face, and we can't quite read the expression. Then we glimpse the mouth, that is, we fixate on the mouth, and we can read the expression on the mouth. Then we come back up to the whole face. We have to know the spatial relationship between the mouth and the face, but because we moved our eyes to do this, we do. We come back up to the whole face, and we incorporate in the representation of the whole face information about the mouth. So here, you thought it was a neutral expression. You looked at the corner of the mouth. Now you think it's maybe a slightly smiley expression. And so you have a vector representation here that's taken the information that came from this glimpse, incorporated into this state, and now you store that state. The fast associative weights store this state that's integrated what came from this glimpse with the bottom-up information for the whole face. Now you go and do another glimpse. You maybe glimpse the left eye, and the left eye doesn't look at all like a smiley eye. It looks like a very unhappy eye. So now you come back up, and what you need to do is integrate the bottom-up information. The bottom-up information is really useful because it acts as a key. It basically dominates what you get here, and so the state you'll get here will be pretty similar to the state you had there. And so you'll get a state that's a key for the associative memory. But now what you can get in the associative memory is going to be influenced by the expression of the left eye, but it's also going to be influenced by what's stored in the associative memory here, if we do one more step to do the retrieval. And so now you've got the information from processing the mouth at high resolution has got into the representation of the whole face here and been carried forward in the fast associative weights. So now at this point you're combining the bottom-up information with this glimpse and with this glimpse. The information in all three glimpses is being combined. Okay, that's the basic idea. We applied that to face recognition on the multi-pi data set, which is lots of different faces, lots of different illuminations, lots of different viewpoints. We used only the near frontal viewpoints. And we downsampled it to 48 by 48. And then we used a fixed sequence of fixations. We're trying to discriminate expressions: neutral, smile, surprise, squint, disgust, and scream. We're using this trick of using a fixed sequence of fixations. So what we do is, and we're assuming that our computer has sort of zoom maybe separate from pan. So we're going to have an outer loop that looks at each of the four quadrants of the whole face. So each quadrant is 24 by 24, but we're going to downsample a quadrant to 12 by 12. So our input's always going to be 12 by 12. So we get a 12 by 12 quadrant, and later on we're going to get the next 12 by 12 quadrant. But as soon as we've done the 12 by 12 quadrant, we're going to go down now, down a level, and look at the four subquadrants in fixed sequence. And then we're going to come back up to the same 12 by 12 quadrant. So each higher level quadrant, each top level quadrant is glimpsed twice, because it's glimpsed once at the beginning, and then it's glimpsed later on when you get the information from lower down. And at the lower level, we're not using the fast associative weights to remember things. It's just a little IRNN that's seeing four glimpses, and it's accumulating information in its hidden state, but it's only for a short sequence. And then when you come up a level, in order to access information stored on previous lower level accumulations, you're going to use the fast weights. That's probably clearer with a picture. I hope you can see this. Is there a way to turn these lights down?
Yes.
It's going to be one of those switches. There, that's probably better. Right. So this is a paper from the figure from the paper. And this is one of the 4 quadrants of the face. And then you go down and you look at the subquadrants of this. By the time you get to the end here, you've got information that you got from looking at the accumulated from the subquadrants, accumulated in the hidden state. And now this is slightly different from what I described, but close enough. You first go back and look at this. So you get a state here from the convnet, and that's going to be your key. And then you use this key to do a retrieval, and then you combine the information that you got with the retrieval. So this state, but modulated by what came back from the fast waits. And that retrieval of any previous information you had here is combined with the bottom-up input. Obviously, you have to know the spatial relationship between this piece and this, but because we use a fixed sequence of fixations, the weights can learn that. If you're using much more flexible fixations, you have to explicitly gate this matrix by whatever the spatial relationship is between the part and the whole when you go back to the higher level. And so here we stored information in the fast waits, and here we're doing a retrieval. Once we've done the retrieval, we've got a slightly different state now, and again we store information in the fast waits, and then we go on. And if you look at how well this works, if you just take an IR and N on this task and look at the error rate with varying numbers of hidden units, with 100 hidden units you can do the task reasonably well. An LSTM is slightly better than IR and N. If you put in the fast wait memory, it's significantly better than the LSTM. It's not as good as a convnet in which you have all this stuff happening in parallel. So because we're using these patches, we could say, forget about the temporal sequence. Let's just give it all the patches at once, so it can see everything at once, like a convnet does. And of course that works better. But notice, given this scanning sequence of fixations, if you're going to do a fixed scan, you might as well put it all in parallel, because you're not saving anything. There's no way you're not looking. The real win from glimpses is that almost all of the image never gets processed at high detail. But because we've thrown away because we're ignoring the task of how you make intelligent fixations, we're not going to get that win. We're just checking that the fast weights can actually be used for integrating glimpses. And so a convnet is always going to do better if you're going to do a fixed sequence of scans that cover everything. But notice that by the time you got to 200 hidden units, this is, I'm sure that's not a significant difference. This is working as well as convnet. Okay, one thing I didn't mention so far, which is very important, is when you use fast weights, you have a training example, and you're adapting the fast weights based on the input. And so the fast weight matrix will be different for different training examples. And so you can't use the trick of having a mini batch where you apply the same matrix to all of the examples of the mini batch. Now, if you're interested in neuroscience, that doesn't matter. But if you're interested in making good use of a GPU, that really does matter. And in fact, I got Ilya to try these ideas in 2011 when he was predicting the next character. It wasn't quite the same because he was setting the fast weights using backprop. And what he wanted to do was explore how, if you have a fast changing component of the weight, you can capture the phenomenon in language modeling that if a word occurred like 50 words ago, it's much more likely to occur now. It's very hard to hold that information in the hidden state. It's very easy to hold it in fast weights. And so he was training the fast weights using the fullback propagated gradient and training them at test time too. So at test time, the frozen weights would be slow. The slow weights would be frozen, but you'd still be adapting the fast weights. So you get this kind of online testing, which gives you much better performance. But he gave up on it because he couldn't use mini batches. And that was such a loss that it wasn't worth it. Jimmy Barr realized that you can actually use mini batches. If the sequence is much shorter than the number of hidden units, then the fast weight matrix will have reduced rank. It'll be the sum of a bunch of outer products. Each outer product will give you a rank 1 matrix. You add them all up, you'll get at most a rank, however many things you added up, matrix. And so it's much lower rank. And that means there's a much more efficient way of doing the computation, which will suddenly become familiar. What we're going to do in our computer, in our neuroscience model, we've got fast weights, right? That's very important. But in our computer, we're not actually going to have fast weights because it ruins the mini-batches. In our computer, we're just going to store some activity vectors, and we're going to figure out what a fast weight matrix would have done. And the way you figure it out is this. When you use the vector as a retrieval key, the vector that you get back is the sum of a bunch of terms, one term coming from each of the previous vectors you had, each of the things that went into creating the fast weights. And as you get further to go, these terms get smaller. And each of those terms is the previously stored vector weighted by the scalar product of that vector with the retrieval vector, but also weighted by the decay factor to the power of how long ago it was. So essentially what you're getting is the current vector is looking back at all previous vectors and saying, I'm going to change myself in the direction of vectors that are similar to me. And if they're very similar, I'm going to change quite a lot in that direction. If they're orthogonal to me, I'm not going to change at all in that direction. And so it's a kind of attention to the recent past, but it's attention to the recent past that doesn't have any free parameters, except for the decay factor. So you don't have to have separate parameters that telling you how to attend to the past. You're just going to be drawn to attractors. You're going to be attracted to previous states. So it's very like what people now use for machine translation, or in general for decoding. When you take an input sentence and you decode to produce the output sentence, as you're producing the output sentence, you want to be attracted to similar things in the input sentence, or you want to use information from things that had similar meaning in the input sentence. So you can think of it as an alternative view of what we've done, is we've shown how something like a brain might be able to implement the attention to the past that you need for things like machine translation without actually storing any activity vectors anywhere. It's exactly the same trick as kept neural networks going in the 1970s, which is psychologists thought you store memories by sort of copying things, and various connectionists said, no, you don't store memories like that. What you do is you change the weights between things so that that thing is easy to recreate. And we've just done that on a fast timescale instead of on a slow timescale. And if you're doing it on a fast timescale, having a simple storage algorithm is fine because you don't need to be that efficient. And so basically, I've managed to bring back 1982 by appealing to 1973. Okay, I'm finished. I think. Yeah, I just said that. And my conclusion is that recurrent neural nets really can do proper recursion if they have this fast weight memory. Real ones in the brain could do it. But we've only really just started exploring how to use extra memory with neural nets. Almost all neural nets just have activities and slow weights. A paper published in Nature today called the Differentiable Neural Computer by Alex Graves and co. from DeepMind is an extension of what they call the neural Turing machine, which has an external memory that stores literal patterns, but they show it doing impressive things. They show how with using that external memory, they can learn algorithms from examples. I think there's going to be a lot of exploration of different forms of memory for neural nets, in addition to the activity patterns and the slow weights. And I think we're eventually going to be able to get neural nets that do what the good old-fashioned AI people want, which is actually reason. Okay, now I'm done. Oh, I want to say one more thing which doesn't seem appropriate in this context, so I'll keep it very brief. Google would like me to use this as a recruiting tool to persuade you all to move to California. So what I'm going to do is just put something on my web page that tells you what Google would like me to tell you. Google might also be interested in some of you staying here. Okay. So if you look on my web page, you can find out about the Brain Resident program where you become a Google employee for a year and you get something like the first year of a PhD if you haven't done a PhD, or the first year of a postdoc if you've done a PhD.
Okay, so some time for questions. So, you're saying at the end.
That was just like my first talk. When I first talked about this stuff, people just looked blank.
So you said at the end about the fast weights being similar in the sense of the attention.
Yes. Their attention to the recent past.
Recent past. So the attention of the recent past is generally works, it's very selective in some sense. So you have to have often information input or dependent on various things to decide exactly what's the attention of the recent past. It's not clearly how you're going to get that.
Okay. So what I showed you was we do one-step retrieval. So you have a vector, and it's going to be influenced by vectors that are similar to it, but there'll be maybe a lot of those that are influencing it slightly. But let's suppose one of those vectors is influencing a bit more than the others. And now think about the power method for extracting the leading eigenvector. You let this vector move a bit towards that one. Now it's closer to that one and further from the others. And so now on the next iteration, if you do several iterations of this associated retrieval, it's even closer to that one. So if you do several iterations, then you can home in on something that you're close to if there's one thing you're considerably closer to than other things. So it can get this sort of focusing of attention over time if you give it several iterations. Jimmy tried that. I think when he wasn't using layer norm, that actually helped. When he was using layer norm, the vectors were spread out enough so it worked fine without that. Yeah.
So in an image, you can I can imagine doing glimpses and then doing high resolution and point point and low resolution and like that. If I want to do a similar thing to text, what is the equivalent of going higher?
I think it's focusing on a subclause and taking a clause and processing that clause, having stored information about the rest of the sentence it's in. So I think that's the equivalent thing. So if you think about the parse tree for a sentence, focusing on a lower part of the parse tree. So in general, almost all the structures in the world, we can make sort of parse trees for them. And these parse trees are deep, like there's the universe, and then there's galaxies, well, there's clusters of galaxies, and then there's galaxies, and eventually you get down to electrons, and then you start on the quarks and stuff. And that's a very deep hierarchy that we understand. But you can't think about it all at once. You take out there in the world, there's this hierarchy. It's a philosophically dubious position, but there you are. And what we do with our brains is we have a little window on that hierarchy, and we move this window around. And that works for all sorts of things. That's sort of what we're attending to at present. Yeah. So, and that's going to be similar for language and for vision and for all sorts of things. And for planning. For planning, you sort of have your overall plan, and then you go off and say, yeah, but can I make this bit of it work? And you figure out that you can make this bit of it work, but only in a funny way, and now you have to come back and see if that works with the overall plan and so on. It's basically the same issue. No, we haven't, but people like Phil Blunsom, there's a paper in NIPS last year where they're storing vectors and then accessing these stored vectors softly. And you can think of this as not exactly what they're doing, but because they want to stack too. This is a way of trying to implement that in a brain without having to store activity vectors to implement something like that. Yeah.
This might be a little bit hand-wavy, but could you think of multiple timescales instead of just...
Absolutely, absolutely. So once you've said synapses change at more than one timescale, why stop at 2? So Terry Sinofsky, when I first met Terry Sinofsky, the first thing he told me was these connections models are silly because they only change each synapses at one timescale. And he was working on frogs at the time, and he had synapses in frogs that changed on very fast timescales. So yeah, you can have multiple timescales.
Which then leads to the analogy of working in frequency space and really doing the same sort of analysis of different frequencies.
I guess, yeah. Yeah.
So you stated that the solves half the problem, but the initial half of how you stand about processing this. So given limit, does the order of entry matter, or how do you?
Okay, so I said that the information in the glimpses is the same whatever order they're in, but obviously if your fast memory is decaying, the order in which you glimpse does matter, because the amount of decay of an old thing will be different depending on the order in which you sample. It doesn't matter, but it matters, but it's not as significant as if the sequential structure really counted, because the sequential structure is stuff you created. Now with video, where you're looking at moving things, then time does matter, because time now is not just an arbitrary thing that you created from a static scene.
So for something like, I mean, this is a little weird, how we replace more biological, but let's say when we have a vision on the actual world, do you think that particular sentence in the learn, or is it actually like more instinct? Like, is there like a more...
Oh, I'm sure we do lots and lots of learning of where to fixate. If you look at someone making a cup of tea, and what you do is you have an eye monitor, and then you project where they were looking onto the video. They'll look for the kettle, they'll start reaching for the kettle. Before they've got to the kettle, they'll start looking for the sink. They'll be picking up the kettle as they find the sink, and then they'll start taking the kettle to the sink, and basically once they've filled the kettle, they'll look for the door of the cupboard that has the tea in, and this is very English activity. So it's very well rehearsed. But what you see is that it's a superbly optimized system. They're starting to get the visual information they're going to need next while they're still finishing the previous action. And they only look where they need to. If you look at people driving round a curved bend, they're glued on the inside of the curve, because that's where information is being revealed. If there's a pedestrian, they make, this was males, if there's a pedestrian, they make one fixation. If it's a woman, they make 2 fixations, and then they come back to the inside of the curve. So if you take the overall objective function, they're behaving optimally. They really have learned how to fixate just the right places. And I remember when I first got to CMU, there was a huge, it was impressive, because there was the mail slots was a kind of 30 by 40 array, or it seemed like that. It was this huge array of mail slots. And you went in the office and you could get your mail, but from the back of the office, outside in the corridor, you could see whether there's anything in your mail slot, if you knew which mail slot it was. And I noticed that after about a week, I would walk down the corridor and I'd just fixate my mail slot in this big array. We're very good at fixating where the relevant information is, and that's got to be a lot of learning. Yeah.
One example where you compare the performance of Faulkner against the learning. So there was a larger data set. We think you would still see a better performance on the fast learning compared to Faulkner, which is why doing Faulkner would learn.
No, I think the performance was the same as ConvNet's. I think that was just experimental error. If you, I mean, Jimmy might want to comment on that. Do you really think the fast weights are better than ConvNets, Jimmy, or do you think they're just asymptoting at the same thing? They're probably the same, right? So they're not beating ConvNets, but they're just managing to achieve the performance ConvNets get by doing everything in parallel. Yes, exactly. Yeah, yeah. What's impressive is that that they can do as well as ConvNets when they look at everything. In other words, the temporal integration is working properly. They're not losing stuff. Yeah.
I think we're all reading that the behavior deals in reference cells of good motion potential.
Yes.
So no one seems to
No, I think everybody takes this into account. I mean, everybody knows that. I don't know why you say that. Anybody who's working on sort of motion knows that. I mean, it's basically, you know the Russians didn't invade Poland yesterday, right? Most of what you know is of that form. This is sort of the frame problem in AI. You know the Russians didn't invade Poland yesterday, and you're very confident of that. And how do you know that? Well, what you know is if they did, there'd have been something on the news, and even if you didn't read the news, a friend would have told you, because it would have been really interesting. And so you know how the world is because you didn't get information, because you've got a monitoring system. And that's what all those motion detectors are about. Most of what's out there isn't changing. If you have a monitoring system that would detect a change if there was one, you can be confident that it didn't change. And that's what's going on. I'm sure they're involved in all sorts of things in the visual system, like getting smooth tracking movements to work properly. But certainly, if there's motion, you're attracted to it, yes. So it's a strong cue that you should look there. If there's some localized motion, you should definitely look there, if there's no other motion. It's, of course, more complicated than that, because if you're outdoors on a windy day, there's all sorts of motion, and it's not just that. Yeah?
Cognitive scientists like Steven Pinker claim that neural nets will never be able to understand natural language, and I think one of their arguments had to do with the inability of implementing recursion. Can we consider those kind of claims debunked?
Yes, they were debunked in 1973.
All right, I think that's a good stopping point. So let's thank Jeff again.
Oh, I should say one more thing. We're going to put this paper on archive very soon.
Okay.
And Jimmy Barr will be the first author.
Great. So one quick announcement. So their next talk is 2 weeks from today. The talks in general are this time Thursdays at noon. And now we're going from the godfather of deep learning to the godfather of reinforcement learning. So Rich Sutton is going to be in town.
2 weeks from today.
I'd like to see you all then. And until then, hopefully go outside and enjoy your lunch and work on training up your fast weights. Okay. Thanks a lot.